Hello everyone. So today I am going to discuss about variance, mean, standard deviation of sum of two random variables. So without further ado, let's get started. Hope you like it. So given a random variable x and y, what is what is random variable? First of all, random variable is just a function from measure space omega x omega. Let's try to use some other letter, say measure space omega with sigma algebra f and measure mu. Okay, so given this measure space, what is the random variable? Random variable is a function from omega to r, where r is Borel algebra. Let's say small sigma algebra consists of open sets generated from open sets in r, open intervals in r. Good. So measurable function from omega to r is called random variable, which I'll be denoting by rv. Okay. So let's say x and y are random variables, so we can consider x plus y, which is a sum of two functions, pointwise addition. So what is expectation of x? It is also known as mean of x. Okay, which is also denoted by this notation. This is nothing but integral of x d mu. Generally, we consider all this thing in a probability setting. So instead of measure mu, we consider probability measure. Okay. In which case, integration dp of a whole space is 1. This probability of whole thing, probability of all possible things which could occur has to be 1. Only thing which can happen is in sample space, no? And hence, this has to be 1. So we can for time being consider, we can thought of mu to be probability measure from now. Okay, in a discrete setting we can consider this particular thing in a following way: pi xi, okay, where xi is all possible values of x is random variable x, and pi is the probability of occurring that particular event. Xi are event. Okay, values of x are called events. Good. So now we can consider, let's say a is a constant, and we can consider a random variable a times x. Okay, since we are considering this particular random variable, expectation of this thing, which we do at times you'll see this notation also, the expectation. Okay, so this thing will be integral of ax d mu, a being a constant from properties of integration. This will be over omega, of course, be a times x d mu over omega, which is nothing but a times expectation of x. Okay, I'll be denoting this particular thing by this notation just to facilitate my life. So we could consider x plus y now, which from properties of integration one can easily see. Integration of sum is sum of integration, no? Yeah, good. So expectation is fine. Now let's talk about variance. What is variance of a given random variable x? Variance is the measure for uh, checking the variability of a variable. Okay, variability of random variable. Okay, so given the data, we like to see how much it oscillates. That would be the right word. Okay, So in order to check the variance of x, how it is defined, it is nothing but expectation of x minus expectation of x, which is mu x, mean of x, and square of it you consider. So this is also a function, random variable. It is just pointwise product of the same random variable and hence the square. So this would give me what? Expectation. So if I consider this particular random variable, since it is pointwise product of same function, I could consider this function is in fact equal to 2 times this function. Yeah, good. Since I'll be using mu x, e of x interchangeably, okay, I'll continue like this. Expectation of sum of random variables is nothing but expectation of sum of the expectation. Constant mu being constant, it will be out as we have seen. And this is constant expectation of constant random variable is constant itself. Okay, it is as if expectation of 1. Expectation of 1 is 1, constant is out, and hence 1 times mu x square is mu x square. Okay, so this boils down to expectation of x square minus 2 times mu x. This is again mu x, remember, we use the same notation. This is mu x square, and hence this is nothing but mu times x square. 2 times mu x square plus mu x is minus mu x square. So you'll often see people writing this way. Okay, so I'll write the same, and hence variance of x is nothing but this thing. Okay, now what is standard deviation? So this is my I'd like to emphasize over here the following thing, that this is expectation of variable x square and this is square of the expectation. So variance is nothing but expectation of square of variables minus square of the expectation. Good. So I'd like to emphasize one more thing over here. Expectation of square of variable is nothing but square. Is not a square of expectations. Okay. Otherwise, variance will always be zero. Yeah. Now, what is standard deviation of x? This is often denoted by sigma x to sigma x. Okay. This is nothing but square root of variance. So now we all know what is variance, what is standard deviation, mean, and everything. Okay, so let's go further. Now suppose I have two random variable x and y, as I said. So I could consider some of those two. Okay, we have already seen mean of some of the random variables, so let's talk about variance. So variance of two random variables is nothing but, as we have seen, expectation of x plus y minus expectation of sum of random variable and square of it. So if we see this thing, what we are going to see is x. Let me just think a bit. Yeah, good. So this is gonna give me what? X plus y whole square minus 2 times x plus y times expectation of x plus y minus plus expectation of x plus y whole square. Okay, and this thing, I mean expectation of, oh yeah, just a minute, x square plus y square 2 times this thing. Okay, so here I forgot to write expectation. So expectation, let me just rub this thing. Expectation of 2 times this thing, and this being constant, expectation of this thing is itself. Okay, So this is nothing but expectation of x plus y whole square plus expectation of x plus y square of it is written expectation of this thing and hence this thing minus 2 times expectation. See, this is constant and this is something which varies. 2 is out, so this is out and expectation of this thing. Expectation of x plus y, expectation of x plus y. Okay, and this particular thing is called covariance of x and y. Okay, in case, good, excellent. So in case x and y are two independent random variables, covariance is going to be 0. Okay, if x and y are independent random variable, this implies covariance of x and y equal to 0. And hence in this case, expected variance, sorry, variance of x plus y is nothing but expectation of this thing plus expectation of this thing, which will give rise to what? Expectation of x square plus 2xy plus expectation. Oh, I committed a mistake over here. This is not covariance. I have to expand this thing. So this will give me what? Expectation of x square using the same rule. Okay, plus 2 times expectation of x y plus expectation of y square minus 2 times expectation of x plus y whole square. Let's see. Okay, and I'm quite confused over here. Just a minute. So this will give me this. Yeah, fine. Oh yeah. Let me think a bit. Yeah, this. Okay. Yeah, in fact, I'm going to do it this way. Okay. This is not going to lead me where I want to go. So just forget this stuff and do it again. So this particular thing, let me just rub it. It is not that I did something wrong, but thing is I want to arrive at some good formula for covariance and hence I'll do it again. So this will give rise to what? So x plus y minus expectation of sum is sum of the expectation. I'll just write in another way. Mu x minus mu y square of it. This will give rise to expectation of x minus mu x plus y minus mu y. Okay, whole square expectation of this thing. This will give rise to expectation of x minus mu x whole square plus 2 times expectation of x minus mu x times y minus mu y. Good. What else? Plus expectation of y minus mu y whole square. So if you remember the definition of variance, this is nothing but variance of x. This is nothing but variance of y, and what is left is called covariance. Okay, this particular thing is covariance of x and y. So you might have seen somewhere this particular formula x minus mu x, okay, y minus mu y over n minus 1. N minus 1 is number of sample points. So when you take mean is nothing but sum of the random values which occurs in random variable, which is assumed by random variable, okay, by number of points in a sample space, okay, in a sample rather, okay. Here at times people consider n, at times consider n minus 1. I mean logic is the following: if we are taking sample, usually one consider n minus 1 where n is the sample size, just to avoid the bias, okay. That's the thing. So here is the thing. Good. So this particular part comes from this and this particular part comes from this. Being expectation, one has to divide by number of samples. That's the idea. So in case x and y are independent, covariance is 0. Okay, covariance basically measures how x and y are dependent on each other. So if you consider data points like, getting off the discussion for some time, say if you consider these are data points, let's say, okay, say xi and y are values of x and y, okay, values taken by random variable, then this is positive correlations. If x rises, y has to rise. If you consider this is negative correlation, okay, negative slope. And if you take, I mean, anything which is like, nobody knows, x rises, y rises, okay, x rises, y might fall, okay, anything could happen. So this is no relation, 0, okay, good. So variance of x and y, variance of x and x plus y is nothing but variance of x and variance of y in case x and y are dependent. And hence, if we talk about standard way, which is the case very often, or which is the case we kind of assume that x and y are independent in our studies of things. Okay, and hence this is quite often the case. And hence, if you consider standard deviation of some of random variables independent, let's say, this is nothing but square root of this thing, and hence square root of, okay, variances of x plus variances of y. So let me write sigma x plus sigma y. So let's say, I mean, we consider some constant random variable and another random variable. If we talk about variance of this particular thing, variance of sum of two random variables, this is clearly independent, okay, because a remains constant, so it has nothing to do with values of x's, which x takes, random variable x takes, and hence this relation would hold true. So variance of a plus variance of y. A variance of a is 0 because a would not vary, okay, and variance of y is variance of, sorry, a key over here a and x. Variance of x is so adding constant to random variable would not make no variation. Okay, difference. Good, which is quite clear. I mean, if you know how much variable oscillates, we add some constant to it. A range of oscillation will not vary. Okay, and hence sigma of a plus x will be sigma of x too. So this thing makes sense when you have two random variables which are kind of different, okay, which are not constant, let's say. Okay. So let's consider now variance of a times x. Variance of a times x, if we consider, then this is nothing but what? Variance of a times x minus mu of a times x, which is nothing but a times mu of x, as we have seen. Mean of a times x is nothing but a times mean of x, square of it. Yeah. So this is gonna give me what? Variance of ax square, okay, minus 2 ax, sorry, 2 times 2 times expectation of ax times a of mu x plus variance of, oh sorry, here it is variance, no? Variance. Oh, what am I doing? This particular thing is expectation. Okay, expectation. Expectation. I did write expectation over here. Okay, sorry for the confusion. The expectation of constant thing is constant itself. So good. Now let's get into this thing. So this is nothing but expectation of ax square. Okay, a square is out. This is x square. See, a is out. This particular thing is out. So 2a square mu x. Expectation of x is mu x again, and hence mu x square plus a square mu x square. So this is gonna give me what? A square out, ex square minus is mu x square. So this is nothing but variance of x. The variance of ax is nothing but a square times variance of x. Good. And hence standard deviation of a times x is nothing but a times standard deviation of x. Okay. So we have seen all we wanted to see. And hence I'll stop over here. Thank you very much for being here. I'd appreciate in case you like the video. Okay. Thank you so much. Yeah, feel free to comment, and if you would like to hear something else, then let me know. If I could do, I'll put a video on it. Thank you so much. See you. Have a great day.